Question 1 says two regions, R and S, are located in the first quadrant. Region R is bounded by the x-axis and the graphs of y equals tangent x and y equals 2 minus x cubed. Region S is bounded by the y-axis and the same two curves. Find the area enclosed by region R. So that's going to be this region down here. All right, so when you do these problems, most of the time, when they tell you to find the area enclosed by like two curves, you're going to do top minus bottom. I say most of the time because that's not the only way you could do it. Another way you can do it is you can do right minus left, like this. Now, you can do it in both ways in this example, but I'm just going to show you the top minus bottom way. Now, when you do this, what's interesting is that there are two top pieces, if you will. The bottom piece is always going to be the x-axis here. So here, let me draw a little line there, right? That's always on the bottom. But what the top piece is changes right here at this point. Right? First, it's the blue function that's on top, and then it's the green function that's on top. So what that means is we're going to end up with two integrals here. We're going to find the area under the curve from 0 up to this point here, and then we're going to find the area under the curve from this point to the end over here. So let's kind of set this up here. We have our first integral. We have our second integral. The first integral, the top function is the blue one, which is tangent x. Then for the second integral, it's the green one, which is 2 minus x cubed. Now we have to find the limits of integration. So obviously we're going to be starting at 0 here, and we're going to be going up to this point. And what I did is I graphed this, and I figured out where this intersection point was. And this intersection point is 0.90216, 1.26575, like this. So we're going to go from 0 to 0.90216. And then for our second integral, we're going to go from 0.90216 to the end over here. So we have to figure out where this end point is. Well, that's just where the green function touches the x-axis. So all we need to do is take 2 minus x cubed, set it equal to 0, and solve for x, which is not too bad. So it looks like we get the cubed root of 2. That's what goes up here. So if you do these integrals and add them up, you should get 0.729. Now, like I said, you can do right minus left here, because if you look over here, the green function is always to the right, and the blue function is always to the left. The annoying thing about this, even though you can do this in a single integral, is that you have to take both of these functions up here and solve for x, which is just a little bit more work. Certainly doable, though. Like you could add the x cubed, subtract the 2, and take the cubed root, and you'd find that x is equal to the cubed root of, let's see here, 2 minus y. So that's what the green function is. If you write it out as x equals, if you take the blue function and do the same thing, this one's a little bit easier. You find that x is equal to the inverse tangent of y. And then when you go to do your integral, instead of choosing the x-axis as your limits of integration, you have to think about the y-axis in terms of your limits of integration. So you'd use 1.26575. So I guess I actually am going to show this to you. So we're going to go from 0 to 1.26575, and then the right function is the cubed root of 2 minus y. The left function is the inverse tangent of y. And then if you plug that into a calculator, you should get precisely the same thing. Part B says find the area of region S. So that's going to be this region over here. And this time we are going to do top minus bottom instead of right minus left right off the bat, because the green function is always up top, the blue function is always below. It's set up perfectly for us. We also took the time to figure out what this intersection point was last time, which is good because we're going to need that for this one here. So we're going to go from 0 up to the intersection point, which was 0.90216. The top function is 2 minus x cubed. The bottom function is the blue one, tangent of x. And then we're going to plug this into our calculator and see what we get. Looks like you get 1.161. And that's our answer. Part C says, if region S is rotated about the x-axis, find the volume of the resulting solid. So what we're going to do here is we're going to come over here, draw a little arrow to indicate that we're going to be rotating about the x-axis. And when you're doing these problems where you revolve some sort of region around like an axis, you're either going to use the disk method, the washer method, or the shell method, although not quite as often the shell method. Here we're going to be using the washer method, and the formula for the washer method looks like this. And how you can know between the difference between the washer and the disk method is you come over here and you find the region that you're rotating, and you draw a rectangle in the shaded region. Now, if the rectangle that you draw touches the axis of rotation, that's the disk method. But if it does not touch the disk, or not touch the axis of rotation, it is the washer method here. So that's how I knew it was the washer method immediately, because I knew that was going to happen by looking over here. Now, the width of the rectangle that I drew here is called delta x, and there's two parts you want to label. You want to label the distance from the axis of rotation to the furthest point of the rectangle, and then the distance from the axis of rotation to the closest point of the rectangle. The longer side is going to be capital R, and the shorter side is going to be little r. So to find big R, in your mind, you can ignore this blue function here. All you have to do is focus on the distance from the axis of rotation to the top of this rectangle here, which is bound by this curve, right? I could have drawn this rectangle anywhere, and depending on where I drew it, the distance from here to here would change. And it changes based off the green function, 2 minus x cubed. A similar idea is going to happen with little r here, except instead of being bound by the top curve, it's going to be bound by the bottom curve, which is tangent x. So once we know what big R and little r are, it's as simple as plugging this into the formula here. I guess we are going to need to know a and b, but we've kind of already done that from before here. We're going to start at 0, and we're going to go up to this intersection point, and the intersection point was 0.90216. That was the x-coordinate anyway. I don't really need the y-coordinate. I guess I'll write it in here since I kind of started with a parenthesis. So when you go to plug this in, here's what I recommend. Always do this. Put in 2 blank parentheses, right? Something squared minus something squared. And then come up here and take what you've already figured out and just fill in the blanks. That way, there's less of a chance of you forgetting the squared piece. I've definitely seen students forget the squared piece because sometimes they will write like 2 minus x cubed, and then in their head, oh, that's the exponent, and they just kind of forget to write it there. And then we're going to go from 0 to 0.90216, and this is what you're going to plug into your calculator. So if you do this, you're going to get 8.331, and that's our answer. If you found this video helpful, you might consider checking out my website, which is linked in the description below. You'll be brought to Infinity Learning Academy, where you can find Cruising Through Calculus. At Cruising Through Calculus, we have over 100 videos and documents to help you get through your calculus class, including videos for each topic, practice problems, and full video solutions for those practice problems. I hope to see you there, and together we can cruise through calculus.